Hey guys, welcome back. This is Abhishek again. After a long time, I'm back again, and today I have brought you a very uh, good notebook I have just created. And this is a pretty basic notebook in NLP, and you might have seen text classification by using machine learning algorithm. But today we are going to do something different. We are going to achieve maximum accuracy we can ever achieve by using deep learning. So today we are going to do spam classification by using LSTM bidirectional model with GPU support. So I will be covering each line by line code from scratch. I will start everything from scratch. Whatever library I will be using, whatever module I will be using, I will cover everything from scratch, assuming that you have very beginner in our deep learning with natural language processing. So let's get started. So first thing first, we will look at what are we going to cover in this video. So first, I will be telling you I will be using LSTM with bidirectional model with some GPU support because we are going to deal with our text classification, and I'm using GPU support to show you how we use GPU support with our LSTM model. And the second thing, I have given these things with no, these are not arranged in any particular manner. I have just written everything and giving some numbers. So second thing I will be covering plotting. So I would be plotting word cloud, how we plot word cloud in NLP, and the second one is NLTK frequency, how we calculate the text frequency, and then we are going to plot some bar plot, and we will be covering text pre-processing because you have always, when you get started with your text data, you always pre-process that, you always remove stop, but you always limitize those things. So we have a bunch of text pre-processing sets, so we will be using a library, a package which owned by me, and I will be showing you how we use that library. So that's very easy, and that's really very important to see, because it will give you everything, like it will do everything for you. It will remove URL, it will remove emails, it will be doing for everything for you. So stick with that, this video I will be showing you that. So I will be covering word to vec by using gensim. So we can use word to vec by using two methods. We can either use gensim, we can use either globe. You don't need to download globe vectors. If you are using Kaggle, you can directly import the dataset from Kaggle. Okay, so that's pretty much I have talked about word to vec. So fifth thing, I will be telling you about embedding layer. We basically use embedding layer in our LSTM. And sixth, not sixth, but it is also a point to note that we will be also discussing how we prepare our data for LSTM. Okay, let's get started. So I have imported a dataset called as spam text message classification. You can just import this data, or you can just simply copy my notebook and you can work along with me. I have given this notebook in my Kaggle account. You can, it's public notebook, you can just copy this whole notebook and you can work along with me. And I will be dropping this notebook in description box, you can check that out from there. Okay, so what I have done here, I have just imported our data set from here, and then okay, so I have written some codes here. I will tell you why I have written this. So let me zoom a little bit. Okay, so here we go. So we are loading essential library. So first I have imported warnings. I have just filtered every warning, and then what I have done here is percentage config inline backend figure format equal to retina. Sometimes in your Kaggle notebook you draw some plots, and that plot, then plots look for blurry, so you have to change the figure format to retina to get the plot in very high graphics in high pixels. So for that you have to do this one. Okay, and then I have written this code percent config completer use gd equal to false. So this is to force auto completion, right? So if you have used your Jupyter notebook, you see that when you press tab, it auto completes, it shows you every method, every module available. So by using this code, you force your Kaggle notebook to do some auto completion, and this is pretty important to do this. Okay, so I'm importing my data from here, you can see here, and then you can see our data set. So it's quite basic to tell you again. So this is, I have done some def.info to just see if there is any null values, but pretty basic thing that it will not have any null values. And this is the memory size which showing up is consumed by using our RAM. So here I'm just taking the shape. So it has 5572 rows and 2 columns. So okay, so what I have done here, so we have ham and spam. So I'm just changing that ham and spam in 0 and 1 by using a dictionary. We can either use replace or we can either use map. So right now I'm using map again. So let's do some plotting, and you can see here our data set is pretty imbalanced. Like you can see there are lots of messages are normal, they are not spam, and only few percent of messages are spam. So since we are going to deal in deep learning, so we really don't need to balance the data set, because we are going to deal with our deep learning, right? So what I have done here, I have created a new column named as a word length, and then I'm applying a function, lambda function, to calculate the word length. So I'm using split so that every space doesn't get counted. So if I just show you on my data set, so it will look like this. Hang it with me. Uh, it must run. What happened with this? Just wait. So you can see here we have counted our word length. So now what we're going to do, we are going to plot this graph by using these codes. So what I have done here, I have just filtered out our category equal to 0, which are normal messages, and then spam messages, and then I'm plotting a word length, right? So it's pretty simple. And if we run this, so we will see this graph, and here this x-axis showing our message length and y-axis showing frequency, and you can see that more bigger message length are used to be spam message. Like if message is pretty huge, then that a more chances that that message will end up with being a spam. So here what I have done here, I have just done some group by and then category and then mean. So you can see that normal messages have average word length of 14 and spam message has average word length of 23. So on this way we can say the one conclusion that the spam messages has more average word length. Okay, so now let's do some pre-processing. So for doing pre-processing, pre-processing consists of removing stop words, lowering every words, every sentences, and we have lots of thing in pre-processing, right? So I'm using my own text hammer library. You can do pip install text hammer. So let me show you how does it work. So if I just search for pip install text hammer, and this is my library. You can install by here pip install text hammer, and this is 0.11. You can see some description how does it work. It has so many method here: remove email, remove HTML tags, remove URL, remove special characters, remove accented characters, making base, spelling correction, and Cont exp means it cont exp, it removes every abbreviation like I dash m, it converts to im, and all these things you must install if you are dealing with natural language processing. I would definitely prefer you to do this. Okay. So now we have installed pip install text hammer. It will install all the dependencies in Kaggle very well. So it need a beautiful soup, it needs our spacey, it need regular expression. Okay, so we have imported text hammer as th, and here I have what I have done here. I have imported from tqdm.tqdm notebook, import tqdm notebook, and then I'm calling tqdm notebook.pandas. So what it will do, it will give you a very nice looking um, uh, it will give you a nice looking bar, time bar, and that will be using by progress apply. So without tqdm you use always apply method, but with tqdm you have to use progress apply, and it will show you a nice looking a nice looking bar here, progress bar, we must say. And I'm creating a text processing function, and here I will pass our data set, and here I will pass a column name. That column need to be processed, or the column which contain our data, text data. So here I'm commenting out our spelling correction because spelling correction needs a long time, and that's why I'm not doing this. So I have done here, and it took some time, and now here I have a nice looking pre-processed data. So again I'm doing some EDA again. So I'm using our frequency dist from n.l.p. So I'm using import n.l.p. I'm creating a word list. So what word list is, I will this is a list which will take every sentence from every entry from our dataset. So for sentence in cleaned df.message, word list.extend, nltk.word tokenize, and sentence, and frequency dist equal to nltk frequency dist and word list. So word list is here a list of list containing words, right? So and a word list is a list of containing all the words from our text data, and then I'm passing that list of words in our nltk freq dist. And now if we run it, it will give us most common or most occurring words of our text data. Now if you want to plot this, what if you want to plot this, then you have to create a data frame by using freqdist most common 30 word count. So I'm plotting this. So now we have got a nice looking plot. You can see the 2 has come maximum of the time, and then u, and then all these things. So now if I want to create a word cloud, so by using this code I can create word cloud, and here word cloud dot stop word, by giving this stop word it will ignore all those stop words. And I have set width, height, and generate from frequencies frequentist. So this is the same frequentist we have just calculated by using nltk.frequentist. Here you can see right here. So we are passing the same frequentist right here. So we will have this nice looking word cloud. Okay, so now we have done plotting, we have done EDA, we have done text pre-processing. Now the main thing start. Main thing is we have done everything, right? So we have done plotting, we have done text pre-processing, we have done almost everything which was common in before, which was really common and basic. Now we are going to enter in our deep learning module. So I must say that module 2 is deep learning, right? Learning. So till now we have done all text processing and plotting. So right now for what the first thing first, I'm going to split our data, right? Because we need a train data, we need a text data, test data. So x train, x test, y train, y test, train test split. I'm using train test split, and then I'm passing our data right here. Cleaned x will be our text body, and clean df category will be 010101, and here test size I'm putting 20% as our test data, and then I'm using stratify because I want my ham and spam ratio to be fixed in our train and test data, right? And then I'm passing a random state, and this is pretty basic. We have done almost many of times we have done this. And now very important thing, we are going to pre-process our data by tokenizer. What it is, tokenizer, a tokenizer is a class which tokenize our word, and it makes a tokenizer object, right? So here I have imported from keras.preprocessing.text import tokenizer, and then I am fixing num word equal to 10,000, right? What is this num word? So suppose we have a text data. Let me just show you something. uh, Suppose you have a very big test data, right? You have a very big data, text data, right? And in this text data you have so many unique words, like you have many unique words. And what tokenizer does, tokenizer arrange them in order of their frequency, right? So suppose this test data has suppose let's say 20,000 unique words, right? This text data has 20,000 unique words, and what tokenizer will do, tokenizer will arrange them in decreasing order of their frequency, means the word which has come more often than that word will be top, and this will be arranged in our frequency based, right? So if we have selected our num word equal to 10,000, it means it will select top 10,000 words in our data, and it will tokenize them, right? So right now we are selecting only 10,000 words which have occur most of the time, right? So we are going to use our 10,000 words as our features, right? So in NLP we say words as our features. So this is what we are talking about. And here a tokenizer we are passing num words equal to 10,000 and lower equal to true. So you can see I'm using tokenizer and passing the num words equal to 10,000. So it will be num words means it will be maximum features, right? And then I'm tokenizer equal to lower equal to true. This will lowercase. And then again I'm creating df total equal to pd.concat xtrain xtest x is equal to 0. I'm concatenating xtrain and xtest because I want to train our tokenizer in our whole word, right? Whole unique word. Maybe some words will be in our test data, some will be on in our train data, some will be in both, but we want to train our tokenizer on every unique words, and that's why we are training our tokenizer, we are passing our tokenizer the every words we have in our data. So this is very simple. So I'm here doing tokenizer dot fit on text because we are training on the text data, so I will be saying fit on text and here df total. So what is our tokenizer right here? So tokenizer is, again I told you, tokenizer is just an object. So this is tokenizer is just an object. So if I do tokenizer dot word index, it will show you the maximum, it will show you the maximum unique words you have available in our data, right? So whatever our model will predict must have these unique data, these unique words must have any unique words, right? So it must have some common unique word, right? So that's why. So I'm just now calculating our maximum word length in our train or test data, in our train data. So right now I'm just calculating and I have find out clean df dot word length max, and it comes out 171, right? So this is the second important step right now I'm going to do. I will say that step step 2, right? So step 2, and this was step 1. So it will be more clear for you to figure out what are we doing in step 1 and step 2. So in step 1 we have done tokenizer, we have created tokenizer, and we had fitted our tokenizer on our text data. And in step 2 what we are going to create, we are going to create our input data, right? We are going to create our input data. So the tokenizer we had fitted, first of all you have to import some from keras.preprocessing.sequence import pad sequence, right? What pad sequence does, pad sequence, I'm taking an example. Suppose you have a very big text data, right? So you may have this much long text, and then the second can be this much, like in this text data someone is saying, hey, this car is free, you can buy, and all these. And the second text may have, hey man, or hello, or something like that. And the third text in our data may have a very long, you can say this is like a long word length. Third may have, hey man, hey hello, or just. But when we will feed this data in our model, then every text data must have equal length, every data must have equal length. So wherever our word have no, like these all are blank, so we will put some 0, we will pad them and make every sentence in equal length. So what we do by using pad sequence, by using pad sequence, we we change every word length, every sentence length equal, we equalize every sentence length, right? So what are we doing here? So imported pad sequence, and then I am converting text to sequence, because we have fitted our tokenizer by calling fit on text. And now what are we doing? Tokenizer dot text to sequence, because we have extrain, the extrain we have is our text. So we are converting this text to sequence by calling tokenizer dot text to sequence. So and I'm places, I placed here underscore. So if I show you what this extrain underscore is, so you will see this is a sequence, right? This is a sequence. So if I just see what this shape has, okay, so this has no shape. Let me, this has no shape because this is a list object. So we have just fitted text to sequence, we converted every text to sequence, and the sequence will have their index, every word will assign with some number. So by calling text to sequence, we are just by calling our tokenizer, what we have done, we have given every word some number, like every unique word, we have given every unique word with some unique number. And then what are we doing? We are calling text to sequence. So in sequence, in text we are giving some sentence, and we are taking out a list of numbers, so that number will be assigned with some unique words, right? Suppose hey is given with 0, and hello is given with 1, and something like that, so that will be unique. So here again extend pad, so we are doing padding. So what padding is, padding equalize the length of the sentence, right? So I'm equalizing the word sentence length to 171, because maximum length we have found out as 171, so that's why I'm giving 171. and this extend is a sequence right here. And then padding, we have padding two method, pre and post. In post, padding is given at the last, at the post. Padding means we will fit 0, right? And the same with text data. Okay, so run this. Okay, here we go. And then if I just show you what we have right now, xtrain pad, so you will see that we have a data with equal length, and you can see here are those zeros, right? So these zeros are actually padding, right? So we have just equalized every sentence to 171 length. And then you can check out that the shape. So we have, this is our train shape, and then we have test shape. So now we have a 2D matrix. We have converted our text data into a 2D matrix. Now we are going to create a model to fit our this data. So we are importing from tensorflow.keras models. I'm importing sequential, I'm importing dense, then LSTM, then embedding the bidirectional embedding layer, and TensorFlow and all these, right? And then I'm also importing CUDNN LSTM and CUDNN GRU, and then dropout. So what CUDNN LSTM and CUDNN GRU is? So CUDNN is basically a GPU supported LSTM model, and I'm importing dropout because CUDNN LSTM doesn't support dropout, so you have to add a different sequential layer for dropout. So here I am giving an embedding dimension equal to 100. So let me tell you something about embedding layer. So what embedding layer does, embedding layer converts every word with some vector, right? So suppose there is a word, let me just show you. You can definitely read about embedding layer on online, but let me tell you something about it. Suppose there is a word, let's say there is a word man, right? There is a word man, and what embedding layer will do, embedding layer will convert this word with some vector of dimension 100. Right now I'm converting dimension to 100. So this this unique word will be represented by a 100 dimension of 100 vector. There will be so many unique numbers, and that those number represent this word. So embedding layer do this. And what is benefit of doing embedding? Because if we have some words correlated, then their vector will be also correlated. Okay, that's why. So here I'm calling model equal to sequential model, add embedding, and input dimension I'm putting as 10,000 because we have already fixed that. And output dimension, this is output dimension, means embedding will output in 100 dimensions, so I have passed here. And input length, as we know, input length is 171, so we have done that here. And this embedding layer will output a 3D matrix, and that 3D matrix will go in our LSTM model, because our LSTM model only support 3D tensors, right? So that 3D tensor will go in our CUDN and LSTM. I'm using 100 units and return sequence equal to true, because we are going to stack our LSTM. So right now here we have just want to stack, so that's why we want to return the sequence which goes in LSTM1, and then it goes to again LSTM, and then goes to again LSTM, because we are stacking 3 LSTM right here. So at the last we have put our return sequence equal to false, and then model equal to add dense equal to 1. We want one output vector because this is this is our binary classification. So the one output will give us a probability, and here activation equal to sigmoid. And then I'm just compiling this model, and matrix equal to accuracy. And here I'm defining some model checkpoint and stop early stopping, so you can see this. and then I'm passing model fit xtrain pad xy train epoch equal to 35, batch size 120. Validation data I'm passing xtest pad ytest, verbose equal to 1, and callbacks equal to early stopping and the model checkpoint, right? So I have just trained this, and you will see that we have ended up with having accuracy of 0.98. So if we plot this by using history embedding, because this returns history, so I have just stored that in a variable, and so we have stored that in variable, and now we have just plot our learning graph. You can see that somehow our train accuracy touching 1, so we can say that this model is slightly overfit, and we are ended up with 98% accuracy. Now the method 2 is we are going to use a word to vec. So what word to vec is more robust embedding method. What embedding method is, we are going to convert any word into some dimension of vector. So that some dimension of vector is going to convert by pre-trained vectors. So here I'm going to use a uh, uh, pre-trained data, and in that data we have some words and their corresponding vectors of their own dimension. So right now I'm using 100 dimension. It means in this data in this data we are going to download globe wiki gigaword 100, means in this data every word will be represented by some vector of 100 dimension, right? And if any word are correlated, then their vector will have very similar, or will have near values, right? So so for downloading our data, for downloading our vectors, you have to import gensim.downloader as API. You can give any name, and the globe gensim equal to, so it will download 128 MB file. So here we go. So what word to vec is, suppose I have just given this a cat, so it will give you 100 dimension of list, 100 dimension of vector, you can say even. So here the cat is represented by our 100 dimension, right? So here cat is represented by 100 dimension, and if I just count their shape, you will see that we have 100 dimension. And now what are we going to do? We are going to convert every unique word we have in our data set into vector, right? To do that, what I am going to create, I'm going to create a matrix, empty matrix np.zeros num word here we have already defined as 10,000, and vector size is 100, because we have decided to download 100 dimension, and if you want to download 300 you can go with that, and that data will be of having 7 to 800 MB, right? So I'm going to go with 100 dimension. You can increase your dimension as you do some more complex model. You do more complex model like emotion detection and all these, you can go with 300 dimension, and 50 dimension if you are dealing some very basic thing, right? So in order to do that, and then we have gensim weight matrix. And then for word index in tokenizer.word index, this is our dictionary. I'm just iterating our dictionary by dot items, and if index is less than numword, because here numword is 10,000 and our index is the their occurrence index is their um, frequency, we can say. And then if word in glow gensim word to vec dot vocab, if word is in our globe gensim, and if word is exist in our model in our gensim word to vec, then I will convert into vector. And if they are not in our word vec, like suppose you have given some random word like MC, so that will not belongs to our global gensim. So in that condition, it will return np zeros with 100 dimension, right? So that vector will be 0 0 100. So that vector will be only 0 0. So if I just calculate the shape, it will give you 10,000 and 100 dimension. Right now again I'm creating our model, I'm creating again our designing our same model, but right now there is some change. Here we are passing, here we are passing weights. Weights will be gensim weight matrix, the matrix we have just created yet, and then trainable equal to false. Trainable equal to false will be, so here trainable equal to false because our matrix we have given, the weight we have given, I don't want the weight to be adjusted because this is already pre-trained weights. And then the whole procedure is really very same, and then some summary, and then I'm just defining some early stopping and checkpoint, and then I'm fitting. And now you can see we have achieved our accuracy in just 11 epochs, and I'm ending with 97% accuracy. And you can see that our accuracy is 0.99, our train accuracy is going up to 99. And if I just plot the learning curve, you can see that we are not having any kind of overfitting or underfitting. We are just going with very consistent accuracy. And I think we should have given some more epochs because this validation accuracy is going upward, so we can achieve some more accuracy. So right now I'm just fitting with 10 epochs. And now what we are going to do, we are just validating, evaluating. So you can see the model gensim, which is trained with pre-trained word to vector. So we are going to have 97% accuracy, and with model with embedding layer 98 accuracy. So now what we are going to do, we are just model evaluating our model. So you can say that you can see here that we are getting f1 score 99 and 94. So here you can see that model predict will return a vector uh, of their probability, like that will have probability, and if probability is greater than 0.5, I will say that that as 1, otherwise it will be 0. So here I'm plotting, and here this is uh, predicted by model gensim. So if it predicted by model gensim, if it is predicted by model gensim, it means we are using word to vec here. And you can see that we are getting 99 fn score and 92 fn score. But you can see here the precision is right here is 1 and precision is 0.99. So I would prefer precision with 0.99 because it has no overfitting, and this is more balanced model, I would say. Okay, now here we are defining a function called predict, and here I'm doing some data processing, like I'm converting our sentence to sequence because our tokenizer has already fitted. So I'm converting our sentence into sequence. Sequence means the word of that sentence will be changed with some unique numbers. And then what I'm going to do, I'm going to convert those sequence into padding. So what padding will do, padding will convert them into 171 word length, and it will convert them into a feedable data to our LSTM. And then I'm predicting model gensim.predict sentence, and if probability is greater than 0.5, I would say that the message will be spam. And np.round, I'm also printing the probability or the percentage surety we have, and else this would be normal. Okay, so right now suppose I'm going to copy this sentence and I'm going to print. Let's run this, and suppose I have given this of no suppose I have given buy new flat at 20% discount, right? Discount, if I just see, you will say that we are 54%, we are 54% sure that this is normal message, because anyone can also say that buy new flat at 20 discount, it is not really spam. But let's say buy a new flat at 20% discount and win ticket, right? So you will see that this is spam, 91% sure that this is spam. So if I copy this, let's run again. uh, f- free entry, free entry to win new phone, and let's run this, and you will see that this is a spam, 75% sure that this is spam. So on this way we can create our text classification by using LSTM and word2vec. I have shown you, and stay tuned. I will be showing you in the next video. I will be showing you how to do some emotion classification, emotion detection, and I will be deploying that on our web server by using I will be converting them into web application by using Flask. So stay tuned and stay safe. Have a nice day. Thank you. Thanks for watching this video. If you like this video, please do share and subscribe. And if you have any question regarding this notebook, regarding this video, please feel free to leave that question in our comment box. I will definitely reply. Thank you.